Okay, so let's dive right into this with a question that honestly might seem pretty simple at first glance, but is actually one of the most profound mysteries of the physical universe. Where does energy go when systems change? Seriously, think about it. When something stops or falls or cools down, what exactly happens to all that energy? Did it just vanish?
Welcome to today's Explainer. I am absolutely thrilled to have you here. Today, our mission is uncovering the secrets of energy transfer. We're going to put on our detective hats and track exactly how energy moves, shifts, and completely morphs its way through our universe. By the time we're done here, you will literally never look at a rolling ball or even a hot cup of coffee the same way again.
All right, here's our mission briefing for today. To crack this case, we're going to cover 1. The Ultimate Energy Rulebook, 2. Stored versus moving energy, 3. The Disappearing Energy Mystery, 4. Tracing energy through systems, 5. Everyday energy engineering, and finally 6. Your exit question challenge. Let's get right to it.
Section 1. The Ultimate Energy Rulebook, the law that governs our universe.
So before we can go tracking energy, we have to know the one unbreakable rule it always follows. This is the absolute foundation for all of physical science, the law of conservation of energy. It states that the total change of energy in any system is always equal to the total energy transferred into or out of the system. What does that mean in plain terms? Well, energy is never ever created out of thin air, and it is never destroyed. Actually, it's a lot like currency in a completely closed economy. You can trade it, you can break a $20 bill into fives, you can change it from cash to credit, but the total amount of money, it stays exactly the same. Energy has to come from somewhere, and it absolutely has to go somewhere.
Moving on to Section 2, Stored versus Moving Energy. Meet the two main characters.
If energy is like currency, well, these are the two main ways it's kept. First up, we've got potential energy. Think of this as energy just waiting to happen. It's stored energy, and it depends entirely on the relative positions of objects that are interacting at a distance. Like, if you lift a heavy bowling ball up to the top shelf of a closet, it has gravitational potential energy just waiting to be unleashed. Then we have kinetic energy. This is the energy of motion. If that bowling ball gets bumped and rolls off the shelf, all that potential energy immediately converts into kinetic energy as it falls. And here's a really crucial detail to remember. This motion energy is proportional to the mass of the object, but it grows with the square of its speed. Keep that little fact in your back pocket. We are for sure going to need that piece of evidence a bit later.
Section 3. The Disappearing Energy Mystery, a misconception check.
Okay, let's set up a quick crime scene, shall we? Imagine you roll a ball across a carpeted room. It rolls for a bit, it slows down, and eventually, it stops completely. This brings us to a classic statement you might hear someone say, or maybe you've even thought it yourself. The object stopped moving, so its energy is gone. Just think about that for a second. The ball had kinetic energy because it was moving. Now it's not moving, so the kinetic energy is zero. Did it just vanish into nothingness? I mean, did we just break the universe's ultimate rulebook?
Busted. No way. Energy never disappears. According to the conservation of energy, when the motion energy of an object changes, there is inevitably some other change in energy happening at the exact same time. The energy didn't vanish, it disguised itself. It transferred. But into what? Section 4. Tracing energy through systems, following the evidence.
It is time to track down exactly where that missing kinetic energy went. Let's walk through the sequence step by step. In step 1, our system starts with initial kinetic energy. The ball is rolling. Then, step 2, forces interact. The surface of the ball and the fibers of the carpet are rubbing against each other. This opposing force is friction. Now, because of that friction, the ball slows down. But remember the rule, the energy can't disappear. So that brings us to step 3. The kinetic energy is transferred into thermal energy. That's right, the friction between the carpet and the ball actually heated up the carpet and the ball by a tiny, almost a noticeable amount. The energy of the rolling ball was literally absorbed by the room itself.
Just to be totally clear here, thermal energy is simply the motion of atoms or molecules within a substance. When kinetic energy from a rolling ball was transferred via friction, it literally made the microscopic atoms in the carpet jiggle around a little bit faster. We measure this macroscopic jiggling as an increase in temperature. So the kinetic energy didn't vanish at all. It just went from the macroscopic motion of the ball to the microscopic motion of atoms. How cool is that?
Section 5. Everyday Energy Engineering. Putting the rules to work.
So now that we know how to track energy, how do we actually use this knowledge in the real world?
Well, let's look at how mass and speed impact total kinetic energy. If we have a base state, say 1 times the mass and 1 times the speed, you get 1 times the kinetic energy. Simple enough. Now, if you double the mass, you simply double the kinetic energy. So a 2,000-pound car has twice the kinetic energy of a 1,000-pound car going the exact same speed. But here is where it gets absolutely crazy. If you double the speed instead, the kinetic energy doesn't just double, it quadruples. It becomes 4 times the kinetic energy. Why? Because as we saw earlier, kinetic energy grows with the square of the speed. This is incredibly important for engineers who design things like car brakes or crash safety systems. A vehicle moving twice as fast has 4 times the energy that needs to be safely transferred into thermal energy by those brakes.
And here's another brilliant engineering challenge for you. Energy spontaneously transfers from hotter regions to colder ones. That's just a fundamental rule of nature. Heat always flows toward cold. Knowing this, we can design devices to completely control that flow. If we want to minimize that thermal energy transfer, we design a heavily insulated box or thermos for your coffee. But if we want to maximize it, we might design a solar cooker to capture and concentrate that thermal energy straight into our food. We can literally manipulate the physical universe once we understand its rules.
Section 6, your exit question challenge. Test your detective skills.
All right, I am officially handing the detective badge over to you. Here is your final challenge for today's explainer. When your hot chocolate cools down, where exactly did that thermal energy go? Remember the rule book? The energy didn't just vanish into the void. It had to transfer. So, did it go into the mug? Did it go into the air in the room? Did it make the atoms in your kitchen jiggle just a tiny bit faster? Next time you make a hot drink, I want you to really think about how you are quite literally heating up the rest of the universe, one tiny molecule at a time. Thanks for joining me today, and keep questioning the world around you.